All right. Hello, everyone. I'm going to present this paper called SpanDB, fast, cost-effective LSM-tree based KV store on hybrid storage. And a lot of authors on this one, but mostly from University of Science, Technology, China, and Qatar Computing Research Institute, and a few others. So it was at FAST last year. And so as we know now, key value stores are pretty ubiquitous, and things, there are many places they are critical for business or whatever, but some examples are online shopping, social networks, even for caching and other stuff. And as we are seeing in papers over recent years, write-heavy workloads are becoming common, maybe even the norm or the majority in some cases. And to service these sort of write-heavy workloads, what we might think of first of all is using an LSM-tree store where we just convert random writes or whatever into large sequential ones, which was very good for a while. But as disks are getting faster and faster, maybe we're seeing this design fall in some places. So a question we can ask is, do these current LSM-tree stores utilize NVMe SSDs well? Because they're much faster and have much lower latency. So can we use all of the disk in current designs or not? And as we know, LSM-tree, we have data that's organized in levels, so level 0 to level K of these sorted files called SSDs. But first, pairs are written to a mem table in memory that's flushed later. But also, if we want some sort of data consistency and recovery capabilities, usually we will write to what's called a write-ahead log. And the writes to this write-ahead log happen even before the write to the mem table. So if we just wrote every KV pair one by one to the write-ahead log, it would be pretty slow. So we have this concept of a group commit. And how it works is that we have a diagram here where on the left we have different threads, and on the top we just have different steps of what we call a group commit. So in steps 1 to 3, we have a number of threads that wish to write to the write-ahead log. So could be just users writing some key value pairs, client threads. And what happens is one will be selected as a leader through some sort of heuristic or something, and it will collect these updates from other threads. So next, after a certain amount of time, or maybe a certain size of updates, the leader will batch these writes together and write them to the disk. And then the leader and the followers are woken up to insert the data to the mem table in memory. And then finally, during this time, we see that at the bottom that we have some thread here, thread 4, which was waiting to make some writes, but unfortunately it didn't make it into the group. Maybe it arrived too late, or the group was closed for some other reason. So it's been waiting the whole time to make its write to the write-ahead log. So when the mem table writes finish, we have these waiting threads that are woken up, and then they can continue. So thread 4 can now make a group or join another group or something like that after waiting. So we see group commit in a lot of stores, not just RocksDB or LSM-tree stores, but there's a couple of issues. First is that this batch step, where we batch a load of writes, of course it makes things faster because we're batching stuff into fewer writes, but it's still one big single synchronous step. And during this time, the disk could be underutilized. The second problem is that when the disks are getting faster, of course, step 4 will get faster, so the whole process will get faster. But now what we see is that in these steps from 1 to 3 and 7, where threads are waiting either to put stuff into the mem table or just waiting to make another group, or just waiting for the mem table writes to finish, we see that these steps start to dominate the time in the entire process. So in the paper, they do some tests and they see that up to 60 to 80% of time spent in sort of write-heavy workloads, or maybe even write-only, are just spent in these steps waiting on a fast disk. And it's analogous to the problem we see with now that disks are faster, the time in the kernel is too high, so we have user space frameworks. Same sort of problem, but in the LSM store. So in this paper, they introduced SpanDB, and it's a high-performance LSM-tree based store, but it's an extension of RocksDB, and it utilizes different types of hardware for different purposes. So we have this concept in SpanDB of a capacity disk that holds the lower levels of the LSM tree on what we can say is a slower, cheaper SSD. And then we have a speed disk, which holds the write-ahead log and upper levels of the tree on a faster disk, so NVMe disk or Optane or something like that. And the speed disk is accessed by SPDK, which is a framework that lets us write to disks quicker by accessing them from user space. And when we're writing the write-ahead log to SPDK, or excuse me, to the disk with SPDK, they introduce this new mechanism of parallel group logging to speed it up. So as a general overview, we have a picture on the right here, and anything in this diagram that's in gray is just unchanged from RocksDB. So we have mem tables that are mutable or immutable in host memory. We just have reads from disk, stuff like that. But on the left here, we have CD. So CD stands for, again, capacity disk, where we have the bottom levels of the LSM tree. So throughout the paper, one of the themes is that we can reduce costs with high performance by splitting the levels between, expensive and less expensive disks. And then on the right, we have the speed disk, which could be Optane or some other fast NVMe disk. And that holds, in this example, holds the write-ahead log and then some upper levels of the LSM tree. And then they introduced this very thin file system on top to migrate or direct writes from levels to either the capacity disk or the speed disk. Another major change from RocksDB is that they introduce asynchronous APIs. So RocksDB at the moment is just synchronous. We just have synchronous write and reads, but they introduce asynchronous stuff. So why do we introduce asynchronous requests? Well, when we have synchronous requests, it can be very hard to use the disk fully. But then we can ask, why don't we just use a lot of threads? Which is what people do sometimes, and it's called thread over provisioning. So we could just use more client threads than cores to try and fully utilize the disk. But the issue with this is that as devices get quicker and quicker, even now with these new NVMe devices, even waking up a thread or putting it to sleep can be slower than the actual request to disk. So this sort of thread over provisioning doesn't really make sense. So in SpanDB, they have these end client threads and then end server threads to process asynchronous requests. And in the server threads, we split them up between loggers and workers. So on the right, we have a sort of overview of how this asynchronous processing works. And the asynchronous get, asynchronous check, and asynchronous put are new in SpanDB. They're not in RocksDB. So we have these read and write worker threads that are just spinning on cores to process reads and writes. And as with RocksDB, if we have some get, but the value is in the mem table, we just read it directly, but if we don't, now we're placing it on this asynchronous queue in the background. And the flush and compaction threads are unchanged. Well, these exist in RocksDB too, but they are changed in SpanDB to use SPDK. So they're flushing and compacting to this. Well, flushing to the speed disk, maybe compacting to the slower disk too, but also the speed disk. And for writes, quite a major change. So when we want to do an asynchronous put, we first place the request in this, what they call the prologue, and then return immediately because it's asynchronous. And then later requests will move from this prologue to the, what we call the queue log here. And requests are taken off this log in groups for their group logging process, which we'll introduce shortly. So since with SPDK we can access this directly from user space, we potentially have much faster and lower latency IO. But even if we just switch to SPDK and keep RocksDB's current group logging mechanism, the disk will still go underutilized because it's just a single-threaded serial synchronous write. Very hard to utilize the whole disk with that, especially a very fast disk. So what they introduce in SpanDB is this idea of parallel write-ahead log writes. And logger threads will take batches of these writes from the queue log in the last slide. So just as an overview, instead of these sequential synchronous writes as we looked at in the group logging process before, SpanDB introduces this concept of pipeline while writes, which can happen in parallel. So we have a series of these write-ahead log write requests taken from the queue log, as we saw earlier, which are allocated these log pages and then sent in parallel to the speed device, or just the NVMe SSD over SPDK. It's a simple overview on this slide, but there's a lot of details in the paper about it, and because it's quite a major change to how RocksDB works. So there's a lot of finer details, especially with how data is handled on the disk in the paper. The other feature of SpanDB is that we can move LSM-tree levels to either the speed disk or the capacity disk, depending on the workload. So on this slide, we have this capacity disk that's holding levels 2, 3, and 4, and we have the speed disk that's holding levels 0 and level 1. So level 0 is just mem tables flushed directly from the host memory. And when we are running some workload, we can monitor, SpanDB just monitors the bandwidth at the speed disk, and then can move direct writes from levels depending on the contention at the disk. So for example, in the first part of this slide, we have the top 2 levels on the disk, judging just by this pointer in the store. But let's say later the workload becomes less write intensive. So when the workload's less write intensive, we have less contention on the speed disk. So maybe we want to move the second level there instead of keeping it on the capacity disk. And when we have more levels on the speed disk, we have 2 benefits. One of them is that if any reads need to go to, for example, level 2 in this case, they will be served from the faster disk. So the read latency will be lower. And the second is that since the faster disk just has faster writes, if we are compacting into level 2 and we have enough bandwidth to use from the speed disk, compactions and stuff will be quicker too. So we are opportunistically moving levels between the disks, to benefit from the speed of the speed disk. And I keep saying moving levels, but they don't migrate data in SpanDB. They just direct new writes depending on this pointer, this level pointer. So nothing is migrated in the background or anything like that. New writes are just directed to the latest, location of this level, whatever disk that might be. So to evaluate, they have this 20-core machine with a lot of RAM. So it's like a server class machine, and they configure the stores, based on this assumption. And throughout the evaluation, they test various types of SSDs. So S in this case just means SATA. It's like a cheaper but larger SSD. It's, that's just a lot slower than the other disks, which are 3 NVMe disks. So we have this NVMe 1 and 2, and then this Optane disk, which has the lowest latency, but is the most expensive. Kind of makes the paper a little bit confusing to present and read, but give it a try. And when compared to other KVs, they compare to RocksDB on blobfs, which is SPDK's file system, and the recent store called Cavell. And throughout the test, they just use the YCSB configuration for key value pairs, so 8-byte keys and 1K values. So first, if we look at write only, on the right here, we have two graphs. It's throughput on top and latency on the bottom. And the black bars are RocksDB and the gray bars or white bars are SpanDB. So if we look at the throughput results, these little markers at the bottom mean, for example, SN2 will mean SATA is used for the capacity disk and N2 is used for the speed disk. And these little markers are just throughout the evaluation. But in either case, we have about 4 or 5 times the throughput, or maybe even above that, the throughput of RocksDB in write only. And it's because the thing we looked at the start of the presentation, the current group logging method just doesn't utilize the disk enough. But in SpanDB, they have this asynchronous parallel group logging to a fast disk through SPDK. So we have what we see here, just much, much higher throughput. We also have lower latency too for the writes. I wasn't very clear on why that is, but my guess is it's just because we're writing with SPDK, it's in general, it's lower latency than going through the kernel. Next, we can look at YCSBA. So we have ZipF and then uniform. Same sort of graphs on the right again, RocksDB versus SpanDB. And YCSBA means 50% read, 50% write. So even with reads, we're still far outperforming RocksDB. The big jump in these graphs with SpanDB is because N1 is an NVMe disk. So in these tests where we have N10, we're using an NVMe disk as the capacity device and then Optane as the speed device. So 2 very fast disks instead of 1 SATA drive for the capacity. But what we can notice here is when we switch to ZipF, from ZipF to uniform, so a ZipF distribution will be like one with very high locality, and then uniform will just be some random one. The gap in performance shrinks between RocksDB and SpanDB. And the reason is that when we have a more uniform distribution, it means requests are spread out on the LSM-tree more. So which means that, more of our read accesses will go to the capacity disk, which is a slower disk. And in this case, just gives the same or similar read performance to RocksDB because that path is generally unchanged in SpanDB. And finally, we can look at SpanDB versus other systems, blobfs and Cavell. A little bit hard to read this graph, but we have RocksDB where we use NVMEs. So RocksDB lets us direct, even in the current RocksDB unmodified, allows us to direct write-ahead log writes to another disk. So they configure RocksDB with the NVMe disk for the capacity and then Optane for the write-ahead log. And then we have blobfs, and we have 2 configurations. So Cavell is like a recent KV store that came out a few years ago in a good paper. It was really, really fast, but it's fully asynchronous. So we have 2 configurations here where one of the main points of Cavell was that it batches requests together and sends them to the disk instead of sending requests one by one. So we have a configuration where the batch size is 1. That means B equals 1. And then we have a configuration here called match, which is where we match SpanDB's performance, but we don't care about latency. So the batch size 1 will be lower latency and lower throughput, but match will be the same throughput as SpanDB. And then we have 100% write in A, B, and E. So A is 50% read, 50% write, and B is 95% read, 5% write, and E is 95% scan. or range query and 5% write. So if we just look at kval versus SpanDB, when we look at this configuration called match, we can see that it's possible for kval to reasonably come reasonably close to SpanDB in performance on the left. So when we're looking at throughput, so we have these graphs here in the blue and the red. But if we look at the graph on the right, it's the latency of the different stores. And if we look at the kval configuration where we're matching throughput or close to matching throughput, we can see that the latency is just much, much higher than SpanDB's. On the other hand, if we look at this configuration where the batch size is 1 and the latency is as low as possible in kval, we can see that the throughput is, it's about half SpanDB's and the latency is still a little bit higher. So in any case, it's not really matching the performance of SpanDB either in throughput or latency, despite it being a really high performing store. What's slightly confusing about these graphs is that blobfs performs worse than rocksdb. I don't really know why that is, but I'll probably have a look at that on my own anyway later. So to conclude, we have these write-heavy workloads that are becoming more and more common that can be deployed on LSM-tree stores, or that's maybe what people think of where to deploy them first. But with these new faster disks, it's very hard to fully utilize them, at least if we're just talking about running one store on the disk, because of these. If we're using some sort of logging, this group comment mechanism might just be too slow. And the SpanDB, they introduced these new schemes where we have some parallel group logging, and we place the logs on a very fast but smaller disk, and while the bulk of the database is on a larger, slower disk, and we can direct those writes depending on the intensity of the workload or whatever. Okay, thank you. That's the presentation.